Now let's expand some of those integrals that showed up in the case of charge transport in metals. Most of this isn't necessarily specific to metals, but you'll see that there's some steps that actually are. So what we've seen is that in general, the charge flux can be represented by an integral that comes out of our Boltzmann transport theory. I'm particularly interested right now in charge transport that's driven by an electric field. So I'm gonna ignore all the stuff that had to do with chemical potential and temperature gradients. All of what I'm gonna do here is gonna be basically what happens if I try and drive charge transport using an electric field. So in that case, the thing that sits in between is obviously the electrical conductivity. One thing I'm going to point out here is that I've added an extra factor of 2 that I didn't have in the previous thing, and that's because there are actually 2 spins available per state of electron in quantum mechanics, and that doesn't really show up unless I explicitly add the 2. The other thing I'm going to do is change the x's that were in my previous equations to z's. Why? Well, basically it doesn't really matter. I'm trying to drive charge transport in the same direction as the electric field. So whether I call it x or z, it really doesn't matter. But it does kind of matter once I go to write things out in spherical coordinates, because z is aligned with one of the coordinates and x is not. All right, so let's write this thing out in spherical coordinates. So what I'm gonna notice is that as long as I have an isotropic material, it'll be pretty easy for me to write this out in spherical coordinates, meaning that I'm going to change from things that are x, y, z to things that are just v and then phi and theta. So I'll write the v integral first. So I'll basically change the stuff that had the volume integral will now be essentially a pi squared dk. At least inside the k portion of the integral, and then I'll have a separate set of integrals in the phi and theta directions, right? So cosine phi, the cosine squared phi comes from the fact that the VG was supposed to be in the z direction. So the cosine phi is the projection of that onto the z direction, and then also integrate in theta. So we're switching to spherical coordinates. Integrals are actually pretty easy to evaluate, obviously. So the integral over theta gives 2 pi, and we've previously done the integral for the cosine squared sine squared, and that turns out to be 2/3. I'm also going to make a replacement. So the integral is supposed to be done over k, all k. I'm going to instead switch, since it's isotropic, I can switch out the magnitude of k for just the energy. And then there'll be a constant proportionality that's basically the density of states written in terms of energy. So if I do that, I'll get an integral that's just an integral over energy, and I can pull out all the prefactors of 1/3 that comes out. So if I pull that factor of 1/3, I'll get an integral that looks a lot simpler. So tau times Vg squared times dFdE times the density of states term, and I realized that I just made a mistake when I was writing this up here. The density of states should appear when I make that variable change. Okay, so and then I guess that is the only thing left in the integral after I'm done. Now what I can do is notice that dFdE, if I were to actually look at that carefully, that's actually just an inverted delta function that is centered around the chemical potential. And so what that means is that integral is actually incredibly easy. Basically all I do is I pull out all of the terms that are in there and evaluate them at the chemical potential. And as I've shown previously, the chemical potential and the Fermi level, to do a very, very good approximation, are equal to one another. So we get a very simple expression that's written based on an evaluation directly at the Fermi level, or the chemical potential, however you want to think about it. So that's a nice expression that we'll use a couple of times, but for a metal we can go a little bit further than that even. So if it's a parabolic band metal, then what we can do is use the fact that V squared is equal to 2EF over M. So let me do a little proof of that. I'm not sure if I've shown this previously. So what I'll do is write out the energy for an electron. So for parabolic bands, that's h squared k squared over 2m. That's for a free electron case. But by definition, the group velocity is just d energy decay, or d omega decay. And you can actually explicitly take that and find that it's h bar k over m. If I then take the square of that, I'll get h bar squared k squared over m squared, which I can sort of separate out terms and identify one term that is actually the energy itself. So that's how I get that thing that is actually shoved inside the parentheses there. The velocity equals 2 times e over m, or velocity squared does. Okay, so let's keep going. So what I can do is I can actually do a little bit more regrouping, because when we were doing our heat capacity calculation, we showed that 2/3 times the Fermi energy times the density of states, that's actually equal to the number density of electrons, which is well known for any particular metal. And so I can take that and regroup it in a particular way that most people normally do, where I'll identify something called the mobility, which is the fundamental charge times the scattering time divided by the mass of the electron. So that's called the mobility. So, in general, the electrical conductivity is thought of as being a product of the number density of electrons times the fundamental charge times this thing called the mobility. Now, what we've done right here is derive that for a metal. So I've used a couple of simplifications that have involved degeneracy of the metal and parabolic bands. But that's actually quite a general way of writing the electrical conductivity that we'll find is valid, or at least is valid for semiconductors and conductors that are not degenerate conductors as well. But in that case, we'll have to sort of redefine exactly what we mean by mass and what we mean by scattering time. They're not quite as well defined in other cases. But I hope you can appreciate how cool this is. I mean, basically, we just derived a formula for the electrical conductivity of a material where the formula is written in terms of things that are physical principles, right? Like the scattering of the electron, the mass of an electron, the fundamental charge, and the number density of electrons that are available in a metal, which are things that you can link to microscopic principles. So this is really like kind of cool, I think.